Let's take a look at this borehole and do some interpretation to the clay in this borehole. By looking at the borehole log, we can notice three things. First, look at here, SPT, the N value would be 0. So it says the SPT sampler penetrating into the ground under the weight of the drill rod and hammer. So we would expect this clay is very soft, very weak. Second thing, look at the SPT2 here. Edberg limits test was done on this sample. And we got the liquid limit is over here. So you can see it's less than 30. So it's low plastic. And also the difference between the liquid limit and plastic limit is very small. So you would expect it's kind of a silt-like clay, very silty clay, and low plastic. So another thing is, if you look at here, the moisture content is this, liquid limit is this. So you can see here, moisture content, natural moisture content is almost the same as the liquid limit. So they overlap each other, which give us another indication of the soil probably would be very weak or normally consolidated. The lab test results will provide more information. So let's take a look at the test results for SPT2. From the test results, we can say that the plasticity index is none, as we expected earlier. It's a very low plastic. And the liquid limit and the moisture content, they are almost same. Even the moisture content is slightly higher than the liquid limit. I think there's some error in the moisture content test, but however, at least give us a ballpark estimate of the behavior of this material. So after we look at this, the important thing will be what problems could happen for structures built on this clay. In the following, I provide 7 aspects to consider in the design. Depending on the nature of the project, engineering measures are required to address some or all of them. The first one is on frost action. We got a PI of none, right? PI equal to none. According to the U.S. Corps of Engineers frost design soil classification, it would be classified as a F4 over here, because it's a PI is less than 12. I have created another video on assessment of soil frost susceptibility. Please watch it if you are interested. The second aspect is when we consider stability. First, we know the groundwater level is over here, and the clay is here. So the clay is above the long-term groundwater level. So we can expect, the clay should be somewhat or lightly over consolidated, just because of unsaturated condition causes suction in the soil. So it suction stress would cause some over consolidation of the clay. However, if we build something on top of the clay, for example, no matter it's an embankment or foundation, whatever it is, under the load of the under future load, this material could be brings to normally consolidated condition. Then, when considering its strength, we should be careful about strain weakening for lightly or consolidated clay. The stress strain curve for lightly over consolidated clay normally would be like this. That's the peak shear strength. It was when the soil is still, when the load is still within less than the over consolidation pressure, pre-consolidation pressure. But once the load exceeds that amount, it will, because of increase of strain, the material will actually get weak. So this is a strain weakening. So when choose the shear strength in the design, at least we should consider the strength at this strain level, at a large strain level. Otherwise, if we use peak shear strength, peak strength, then it could be very dangerous. Another thing is maybe we need to consider to use remolded strength. The remolded strength will be even lower. The reason for that is because the moisture content is 25.5, 25.1, right? We saw it before. And the liquid limit is 25. So this is the indication of high sensitive clay. If it is, but we need other data to confirm that, right? But if it is highly sensitive clay, so it would be appropriate to use a remolded strength depend on the expected strain level or movement level of this clay. Third one is about liquefaction. This clay material would be liquefiable. Well, of course, it depends on the level of the ground shaking or ground motion. But without consider that, purely looking at the behavior of the soil, it would be liquefiable soil. If we look at the chart, provided by Bray, we can say that this zone, that's the soil properties fall in this zone will be susceptible to liquefaction. What's our data? Our data is plasticity index. We have none, right? We have none. Remember, we have none. And water content liquid limit ratio, we got approximately 1, right? Because the moisture content, we have 25.1, liquid limit 25. So we got actually slightly greater than 1. Then, so our data would be for, the data for our soil would be for over here. So it is within the liquefiable zone. So according to that, the site classification, the seismic site classification would be class F, right? According to the building, that table provided in building code. I have created another video on seismic site classification. You can watch it if you are interested, so that you know why we classify this site as a F. For the liquefiable soil, when we do stability analysis for the under dynamic load, we need to use its residual shear strength, because of ground shaking would bring down the shear strength to its residual level. For the low plastic clay, liquefiable low plastic clay, it would be the remolded shear strength. So in order to get the remolded shear strength, field vane shear test is required. Also, because the site is class F, so according to the building code, site-specific site response analysis is required. In order to do the seismic site response analysis, we need additional information. First would be the find out the design spectrum for the project site. Second would be the ground motions, the time history for acceleration, and then we need to do some process the ground motion time history, and then scale it to the design spectrum for the subject site. Then we need the dynamic soil properties, especially the shear velocity profile for the site. So at least those are the 3 things required for site response analysis. In the future, I will create another video on site response analysis. But right now, I don't have time to do it. The third aspect is about settlement. No matter it's a foundation or embankment or other structures. When we do the settlement calculation, a very important thing is first identify whether this clay is normally consolidated or overly consolidated. As we mentioned before, the clay should be lightly over consolidated, lightly over lightly over consolidated. In order to calculate the settlement, then we need to determine the pre-consolidation pressure, because this is the most important parameter when calculating the settlements. Of course, the other parameters, CC and the CR, is required, but comparing to pre-consolidation pressure, this one, the pre-consolidation pressure has the most biggest impact to the calculation. For a clay, for the soft clay like this, in order to determine the pre-consolidation pressure, constant rate of strain test is preferred. If we want to do reasonably accurate calculations, we need a pretty refined laboratory test program. The next is about deep foundations. If we use deep foundations to support the structures at this site, there are several things we need to consider. First is where is my pen? Okay. First is the negative skin friction. Because of the soft clay, and if we, for example, if we install a pile over here, that's a very ugly pile. Anyway, and normally we need a little bit of fill over the site, because you know, the clay will be too soft for construction, right? So at least we need some fill, or maybe we need to remove the a little bit in the upper portion, and then put some fill. Then, you know, under the load of this fill, the clay will consolidate, will settle. When it settles, it drags. We have a drag down on the sides of the pile. So we need, in the design, we need to consider negative skin friction. If we decide to use driven piles, then we need to watch for the ground heel, because this clay is very soft, and the moisture content is close to liquid limit. Under the shaking, under the driving, this on one side, the strength of the clay will be reduced significantly. On another side, because of its clay, when we replace the clay with the pile, the ground will tend to be pushed aside from the pile. So that will cause a ground heave. If there's a surrounding structure, existing structures very close to the location driving the piles, then this could damage the existing structure. If we decide to use drilled cast-in-place concrete piles, then during the construction, you need to watch out the squeezing of the drilled hole before you placing concrete. Because potentially you can, because the clay is very soft, and it could have squeezed into the hole. Definitely, casing will be required. Sixth aspect, what I can think of is if we have a deeper excavation in this material. For example, that's the depth of the excavation. If we excavate in this material, so we need to be cautious about the first thing is we need a shoring to support the excavation. The shoring must be embedded into the underlying this sand material a few meters. This is a pretty good material. You can see 30, 34, 45. So it should be embedded into this material. Otherwise, the toe, if you leave your shoring just over here or very short, or just insert into the sand a very short distance, then potentially you can get a kicking of the toe. So it should be inserted in the sand of a few meters. Another thing is because the clay is very soft, if we don't limit the movement of the shoring wall, for example, if we allow it to move like this, and then the ground behind the wall will be something like this. So the volume over here will be approximately the same as here, because this is basically the undrained deformation. So if there's a structure over here, if there's an existing structure over here, so that's the excavation could cause problem to the existing structure. Another thing is because of potentially this material is highly sensitive, so under large movement, it could reduce its shear strength to remote shear strength, and then cause a flow slide. So those are all the aspects we need to consider. It may not be really highly sensitive clay, but purely based on the data we have, we should prevent that, or we need an additional test to verify, to confirm it is not. But based on the preliminary data we have, those are all basic index properties. We should expect those engineering problems. The last aspect I can think of is fill material. It's not a good material for fill. There are several things. First, you can see it's even this material is called clay, but it is very close. You can see it is very close to the CLML zone. This zone, that's low plastic clay transition to low plastic silt. I would expect the material is more or less silt-like behavior, have such kind of behavior. So for this material, we know for silt material, it's very hard to control compaction in the field, because silt material is very sensitive to moisture, uh, to more is very sensitive to moisture change. Another thing is we need, because the liquid limit is 25, more natural moisture content is 25.1, so the material is too wet for construction purpose. So moisture conditioning is required. It's a must. It has to be conditioned before we can use it. It's the in situ state is just too wet. Secondly, we just discussed that silt, because it's silty, very silty, more like a silt. So if we use it as a fill material, this material will be very sensitive to moisture change. So very hard to control its compaction in the field. This material cannot be used as a engineered fill to support a structure. If we use it for fill, it can only be used as, for example, at areas just for landscaping or grading, or the fill at a very depth. Do not directly support any structure. Okay, so that's all I can think of for this clay, based on very limited basic lab test results and in situ test results. So hopefully this is helpful to you. And if you have any other insights, please feel free to leave a comment below. Okay, that's all for today. Thanks for watching.